Hello, I am Benjamin Granger, and I am here with Mohammed Al-Mohish, Catherine Bordelon, and Christian Burley to present to you a simulation of hydraulic fracturing in tight rock reservoirs. Our project explores the methods and creation of a three-dimensional hydraulic fracturing model, as well as providing a data analysis of hydraulic refracturing operations. To begin, we will discuss the goals of our model, its application, and the industry's need for an accurate model. Our interest in this work is investigating the effects of hydraulic fractures as well as subsequent refractures have on a reservoir's productivity. Hydraulic fracturing has been proven to be very successful for unconventional reservoirs. However, the enhanced production is not sustained over a long period of time. This is due to proppant embreadment, principal stress distribution in the reservoir, and interactions with natural fractures. The current low-price environment in the oil and gas industry has forced companies to focus more on developed resources as opposed to drilling new prospective projects. Refracturing is a convenient restimulation method that can remedy the inevitable production decline that occurs after a hydraulic fracturing treatment, but the implementation of this technique is not as popular as expected due to a lack of applicable models. It could be a very effective method if we knew when it would work, but we don't due to a lack of applicable models. We aim to extend our model to simulate the initiation and propagation of second-generation fractures after the depletion of the initial hydraulic fractures. This is dependent on the amount of data we acquire and analyze, as well as the time frame of reaching our project goals.
In order to solve our problem and develop our idea, some initiatives were needed to be taken. So, as a team, we came up with several strategies to resolve our funding, and we did it by contacting my sponsoring department explaining the proposal, which arrived to getting the needed amount of funding. We were able to obtain the production data by drilling info. The information of the typical procedure cost is specified by the percentages divider from the U.S. Energy Information Administration 2016 paper. The reasons for us to determine why do we need that much data is to make sure that our model is mostly applicable on various plays in the U.S., overcoming all the complications and figuring what does this procedure depends on to get it through. Through our obtained data, we concluded that the amount of chemicals needed does a noticeable change to refracturing cost. Leaving off with Catherine.
So we chose to use XFEM-based CZM for our model, which is a blend of the extended finite element analysis and the cohesive zone method. XFEM allows an arbitrary, solution-dependent propagation path in which the mesh is independent of the fracture. This makes the simulation much easier as remeshing is not required. XFEM incorporates enriched functions in the crack domain to account for the displacement across crack surfaces and the singularity across the crack tip. The cohesive zone method allows the use of phantom nodes to incorporate traction separation cohesive behavior and allows the crack to move between element boundaries. This is a picture of the phantom nodes that are placed coincident with the real nodes around the initial crack. These nodes will be used to calculate crack initiation using damage for traction separation criteria, such as maximum principal stress. Since fracture geometry is dependent on several variables that are specific to each reservoir, numerical simulation is used to predict fracture propagation and interaction under varying circumstances. Current models have been able to show stress anisotropy and fracture interactions on single-stage-sized scales, limiting the use of the qualitative results. Because only a small-scale version of a hydraulic fracturing treatment is modeled, there's no way to use the results of these simulations to gain specific insight into the capabilities of an induced fracture network. In order to understand how to implement XFEM-based CZM in Abaqus, we ran a simplified model with an initial crack length that was unrealistically large, but converged very easily. After successfully simulating XFEM in this model, We made changes to the model to make it more realistic. Our project involves the construction of a 15-cluster model in Abacus using XFEM-based CZM to simulate fracture propagation in a three-dimensional setting. The model allows a reservoir's specific parameters to be input, such as pore pressure, porosity, permeability, maximum and minimum in situ stress, Poisson's ratio, Young's modulus, critical energy release rate, damage initiation stress, and leak-off coefficient. We've used average shale values for our model, which will simulate 5 stages of a hydraulic fracturing treatment, each with 3 clusters, and the subsequent depletion of the reservoir. We chose to model a field-scale reservoir in order to get an accurate look at how each stage, and each cluster individually, affects one another. Though this is computationally expensive, we chose to use reduced integration elements around the enrichment zone, as well as coarser mesh density in this region. Because we do not expect crack propagation in these regions, we assume this design choice will be beneficial. The 5 stages are each separated by a partition boundary. This boundary is used to define the crack domains and enrichment zones for each set of clusters and has no effect on the total stress field or crack propagation path. Typical pump time for one stage is 2 hours, but to minimize computational expenses, we have set the pump time for each stage equal to 1 hour. The current 15-cluster simulation has gotten through the first 800 seconds of one 3600-second stage. From this point, we can already see the evolution of fractures and the stress distribution around the fracture. By increasing the injection rate 500 times between 2 simulation trials, we saw that with a higher injection rate, fracture growth is concentrated mostly in height, then propagates through and increases width. The lower injection rate seen here also shows more defined fracture initiation around the initial crack, but does not exhibit as much height growth. Results of the simulation can be used to determine changes such as stress reorientation and fracture initiation and propagation. By importing the fracture geometry created in our simulation into a reservoir simulator, pressure transient analysis can be used to determine fracture conductivity and possible refracturing. Parametric studies will be done to see how injection rate, pump time, viscosity of fracturing fluid, and cluster spacing affect fracture propagation.
Data will be organized by API number, well coordinates, reservoir type, pre and post refracture production, and the folds of increase. Once all the data has been compiled, the well coordinates data will be input into a master graph of the well's location to show which reservoir each well is located in. All of our wells being analyzed are located in the Permian and Delaware Basin on the New Mexico and Texas border. This graph, obtained from drillinginfo.com, shows the monthly production data of a well from Concho Operating, located in New Mexico. The graph shows a production decline through July 2016 when it was shut down and refracked. The refract increased oil production from 1388 to 1568 barrels of oil and 14.066 to 16.828 million standard cubic feet of gas in the month immediately following refracture operations. Once all the wells have been successfully identified, another chart would be constructed similar to the one above, showing the FOI, or folds of increase, for each well in the given reservoir. To successfully identify refracture candidates, we'll be using data from drillinginfo.com and IHS. Wells will be identified by locating data that looks similar to the slide previous to this one. Once wells have been selected, production data will be compiled to illustrate the FOIs. We are hoping to extend this to form a map showing stress anisotropy in multiple reservoirs. Our project is currently on schedule as we have successfully allocated refracture data and begun analyzing it. We plan to have the analysis finished by the end of March. The preliminary XFEM simulation has been completed. The field scale model has been built and is currently running. This month we will decide whether or not our simulation will be able to be extended to refracturing giving time and computational expenses. In conclusion, our data analysis will be able to provide a better look at the variables involved with refracturing treatments, as well as their effect on the overall success of a job. Our simulation will be able to show a field scale approximation of the changes that occur in a reservoir during a hydraulic fracturing treatment. This work can be extended to show refracture entries after depletion of the initial hydraulic refractures, as well as the interaction of batch fracturing or zipper fracs. By matching historical data with our simulation, we aim to have a basic model that can be utilized to accurately identify wells that are viable refrac candidates and their expected producibility. Here are our references, and we would also like to thank Dr. Gupta and her PhD student, Hope Asala, for their guidance and dedication through this project. Thank you.